Right now, over 15 billion miles away in the freezing dark of interstellar space, there is a organs just to stay alive.
Yeah, literally shutting itself down piece by piece.
Exactly. The telemetry data we're looking at paints this picture of a survival story that just defies every original expectation of depth space engineering. So, welcome to the deep dive. Today is May 18th, 2026. And humanity, meaning you, me, and literally every other person currently anchored to this rock, is on the precipice of a mind-boggling milestone.
It really is.
Because very soon, later this year, the Voyager 1 probe is going to be an entire light day away from Earth. 24 hours of light travel.
Which is just an unfathomable distance.
It is, but what makes this so compelling isn't just the cold, hard reality of the physical engineering, it's the juxtaposition of that failing, freezing hardware with this profoundly fragile, intensely emotional time capsule it carries. Specifically, there's a hidden love story literally physically encoded into the spacecraft's payload. Okay, let's unpack this.
It really is the ultimate tension between the macro and the micro. I mean, we have this machine launched nearly 49 years ago, right? Late summer of 1977. And it's currently operating in an environment so hostile and remote that our terrestrial intuition completely breaks down when we try to comprehend it.
Yeah, our brains just aren't built for it.
Right. And yet, housed inside that titanium and aluminum architecture is the most delicate biological and emotional record of our species.
But to really get to the weight of that biological record, we need to map out the current state of the vessel carrying it, right? I was looking through the recent Jet Propulsion Laboratory engineering updates, and the power margins they're dealing with are terrifying. NASA describes them as razor thin, but honestly, even that feels like an understatement.
Oh, absolutely. It's a severe cascading power crisis,
Right.
which is, an inescapable function of physics. When you launch a spacecraft that far from the sun, solar panels become entirely useless. The photon density out there is just negligible. So Voyager operates on a radioisotope thermoelectric generator, an RTG.
Which relies on the natural radioactive decay of plutonium-238.
Exactly.
And I always find it fascinating how passive that system is. Like, it isn't a nuclear reactor.
It's not at all.
There are no moving parts, right? No control rods. It's just a sphere of plutonium generating immense heat through alpha decay, and then thermocouples surrounding it just convert that heat differential into electrical voltage.
You've hit on the exact mechanism there, and unfortunately the exact vulnerability. The Seebeck effect, which drives those thermocouples, relies on the temperature difference between the hot decaying plutonium and the cold of deep space.
Right.
But the power loss we're seeing, which is roughly 4 watts every single year, it isn't just because the plutonium is depleting. I mean, the half-life of plutonium-238 is about 87 years, so there's still plenty of thermal energy left.
So what's failing then?
The critical failure point is the degradation of the silicon-germanium thermocouples themselves. The constant, intense heat literally alters their crystalline structure over decades, making them less efficient at converting that heat to electricity.
Oh, wow. So it's a dual decay. The fuel is cooling down, and the actual engine translating the heat is degrading at the same time.
Exactly.
Which brings us to the breaking update from just weeks ago, April 17th, 2026. The power budget got so tight that NASA had to send commands to shut down the LECP instrument on Voyager 1. And that just feels incredibly severe.
It is. It's essentially a triage situation. They're deliberately blinding the spacecraft to save its central processing core.
Yeah, I kept thinking of it like a hiker in freezing temperatures, systematically shutting off blood flow to their extremities just to keep their core organs alive. But is this the beginning of the end or just a new phase of survival?
Well, triage is the accurate framework here. The low-energy charged particles experiment, the LECP, was arguably one of the most vital instruments for understanding the interstellar medium.
Because it measured the cosmic rays, right?
Right. It used solid-state surface barrier detectors to measure the pitch angle and energy distribution of cosmic rays, ions, and electrons. So for 49 years, it provided this continuous dynamic map of the particle pressure fronts outside our solar bubble. Shutting it down means we are permanently losing that stream of dynamic environmental awareness.
And the way the LECP operated was heavily mechanical, wasn't it? Like, it wasn't just a static sensor sitting there?
No, it utilized a small stepper motor. To get a full 360-degree view of the particle flow, the motor physically rotated the sensor platform in discrete steps. But what reveals the profound optimism of the JPL engineering team is that when they sent the shutdown command, They deliberately left that tiny stepper motor running,
Wait, really? But it draws power, doesn't it? Like half a watt, if I remember the schematics correctly.
roughly half a watt, yeah. They opted to keep it energized on the infinitesimal chance that they might somehow harvest enough power from another system in the future to turn the solid-state detectors back on.
Oh, I see.
Because if the motor freezes in the ambient cold of deep space, the instrument is useless even if they get power back. So by keeping the motor spinning, they're basically keeping the door cracked open.
Leaving a half-watt motor spinning as a monument to hope? I love that. But holding out hope doesn't solve the immediate math problem, obviously. The bus voltage is still dropping, which is forcing the engineering team to plan something incredibly aggressive. They're finalizing a maneuver for this summer 2026 called the Big Bang Fix.
Yeah, the terminology is very apt because of the temporal constraint. They need to buy Voyager about a year of thermal and electrical breathing room. And the strategy involves shutting down certain high-draw active systems and simultaneously booting up lower power fallback equivalents.
But doing that simultaneously on a 49-year-old power bus? That seems like a recipe for a catastrophic voltage drop. Like when you swap heavy electrical loads in your house, you get transients, right? Spikes and dips.
Right, exactly.
If the voltage drops too low, even for a fraction of a second, doesn't that trigger the spacecraft's fault protection system?
That is the core engineering peril of the Big Bang Fix. The onboard computer is highly sensitive to bus voltage anomalies. If it senses a drop, it assumes a fatal short circuit and autonomously starts shedding loads to save the core.
Which could be disastrous.
Totally. The engineers have to time the command sequence so perfectly that the capacitive load of the new system engaging exactly balances the inductive drop of the old system shutting down. And they are doing this blind over an immense communication delay. That's why they're testing it on Voyager 2 first, likely around June.
Because Voyager 2 has slightly better margins.
Voyager 2 has a slightly healthier power margin and is closer, making it the more viable testbed before they risk Voyager 1.
Testing it on Voyager 2 makes total sense, but we really need to quantify the anxiety of that communication delay. It fundamentally alters the nature of problem solving, and we saw this play out vividly during the transmitter drama back in October 2024.
Oh, the October anomaly. If we connect this to the bigger picture, it remains a masterclass in deep space crisis management.
Right. So they sent what should have been a completely routine command to cycle a heater, but the execution of that command caused a localized voltage dip, which tripped that exact fault protection system we were just talking about. And the immediate consequence was that the deep space network on Earth completely lost Voyager 1's signal. The X-band transmitter just went dark.
Because the fault protection logic is ruthless by design. It recognized an energy overdraw and autonomously lowered the modulation rate of the X-band traveling wave tube amplifier.
So it throttled itself.
Exactly. The DSN array down on Earth, specifically the 70-meter dishes in Madrid and Goldstone, they managed to lock back onto the carrier wave eventually, but they couldn't extract telemetry. And then a day later, the fault logic triggered again, completely severing power to the X-band amplifier.
And forced the spacecraft onto the S-band transmitter. I had to read the technical logs twice to believe it, because the S-band transmitter relies on an entirely different, much lower frequency. And it hadn't been utilized for Earth communications since 1981.
Since the early days of the mission, yeah.
It had just been sitting dormant, drifting in the thermal vacuum of space for over 4 decades.
It is a profound testament to the over-engineering of the 1970s. But the challenge is, the S-band frequency intrinsically carries much less data and broadcasts at a significantly lower power level.
Right.
From a distance of over 24 billion kilometers, the signal reaching Earth was on the order of zeptowatts, a fraction of a billionth of a watt. The thermal noise of the Earth's own atmosphere is literally louder than the S-band signal.
That's insane. So the cryogenic cooling systems on the DSN antennas had to be working flawlessly just to distinguish the signal from the background microwave radiation of the universe?
Precisely.
But finding the signal was only half the battle, because this brings us to the ping delay. It takes nearly 23 hours for a radio signal, traveling at the absolute physical speed limit of the universe, the speed of light, to reach Voyager 1.
And another 23 hours for the telemetry confirming receipt of that command to travel back. So you are operating with a 46-hour feedback loop.
I always try to contextualize that for people. Imagine your computer freezes up, you press Control-Alt-Delete, and then you have to sit in your chair for 2 entire days just to see if the task manager opens.
Yeah, it's agonizing.
And if it didn't, you try another keystroke and wait another 2 days. The psychological endurance required of the JPL team is just staggering.
It completely removes the instinctual, iterative troubleshooting process we rely on in terrestrial engineering. Every single command must be modeled, simulated on ground hardware, and vetted by multiple flight directors. Because a single typographical error in the hex code could brick a spacecraft you won't hear back from until Thursday.
Yeah, and looking through the public commentary from the sources covering these updates reveals a lot about human psychology, honestly. The reactions to this 46-hour ping delay and the fact that we're talking to a 1977 computer on the edge of the solar system, they are intensely
Oh,
polarized.
for sure. When presented with timescales and spatial distances that dwarf the human experience, the public reaction usually bifurcates into profound awe or intense skepticism.
Right, you see massive amounts of pride, engineers and lay people marveling that a machine built with wire-wrapped logic boards is outlasting modern, planned obsolescence hardware. But then you have a highly vocal contingent aggressively questioning the mission's architecture. They constantly ask, why NASA didn't launch a breadcrumb trail of relay satellites to boost the signal over the last 40 years.
Which demonstrates a fundamental misunderstanding of celestial mechanics and mission scope.
Right.
Voyager was a planetary flyby mission targeting Jupiter and Saturn. The Grand Tour trajectory was a matter of orbital alignment that only occurs once every 176 years. Launching relay stations would require matching Voyager's immense heliocentric escape velocity, which requires massive launch vehicles for every single relay, multiplying the cost and introducing hundreds of new points of failure.
It's just not how orbital mechanics work. And beyond the armchair engineering, there's a distinct subset of comments that flat out deny the reality of the mission. They reject the concept of the vacuum of space, they debate planetary models, they argue that surviving in those thermal conditions is a fabricated hoax. And obviously, we aren't validating those conspiracy theories here, but the existence of that denial is fascinating.
It really is.
It suggests that Voyager forces humanity to confront concepts of infinite distance and absolute isolation, and the human brain's defense mechanism against that existential dread is sometimes just outright denial.
It's a cognitive rebellion against our own insignificance. Acknowledging Voyager's reality requires acknowledging the sheer, terrifying volume of the void it is traveling through.
Well, let's actually map that void because we throw around terms like deep space and the edge of the solar system, but space isn't just an empty, homogeneous vacuum. Voyager is navigating a highly complex physical environment.
To map the geography, we really have to look at the primary energetic forces at play, namely the interstellar medium and the heliosphere. The interstellar medium is the environment of the Milky Way galaxy itself. It's a vast ocean of ancient hydrogen, helium, cosmic dust, and highly energetic cosmic rays generated by distant supernovae.
So it has its own pressure and its own magnetic flow.
Yeah.
And our sun is moving through it, right?
Yes, our entire solar system orbits the galactic center at roughly 230 kilometers per second. And as the sun moves through the interstellar medium, it's constantly blowing out the solar wind, a highly energized stream of plasma, electrons, and magnetic fields. This solar wind pushes outward in all directions, carving a massive cavity into the interstellar ocean. And that protective cavity is the heliosphere.
The bow shock analogy is the best way I've found to visualize this. It's like the sun is the prow of a ship moving through the ocean of the interstellar medium. The solar wind creates a wake, a physical displacement of the galactic material. But as Voyager travels outward from the sun, it doesn't just suddenly pop out of the bubble. It has had to navigate an incredibly turbulent boundary zone.
Exactly. The transition from the solar domain to the galactic domain is characterized by distinct magnetohydrodynamic milestones. The first major boundary Voyager encountered was the termination shock.
Because the solar wind is moving radially outward from the sun at supersonic speeds, usually around 400 kilometers per second, right? But it can't push against the galactic pressure forever.
Precisely. At a certain distance, the outward pressure of the solar wind becomes equal to the inward pressure of the interstellar medium. So the termination shock is the distinct violent boundary where the solar wind abruptly decelerates from supersonic to subsonic speeds. The plasma compresses, it heats up, and it becomes highly turbulent.
And Voyager 1 hit that shock wave at roughly 94 astronomical units, nearly 100 times the distance between the Earth and the Sun. And once it punched through that shock wave, it was in the heliosheath.
Right. The heliosheath is the transitional outer skin of our solar bubble. It's characterized by slow, dense, compressed solar plasma interacting directly with the cosmic rays leaking in from the galaxy. So Voyager spent years traversing this zone until it reached the ultimate physical boundary, the heliopause.
The absolute edge.
The heliopause is the stagnation point. It is the exact surface where the outward pressure of the solar wind drops to zero against the crushing weight of the interstellar medium. Beyond that surface, the solar wind ceases to exist. You are officially in the undisturbed waters of the galaxy.
Wow.
Voyager 1 breached the heliopause in August 2012, measuring a sudden, massive drop in solar particles and a corresponding spike in galactic cosmic rays.
So it is out there. It's swimming in the ocean between the stars, which perfectly contextualizes the milestone we are hitting this November, one light day, 25.9 billion kilometers. The fact that human hands bolted together a chassis of metal, strapped it to a Titan III rocket, and shot it so far away that light itself takes a full diurnal cycle to reach it, it just defies adequate description.
And its journey is only in its infancy. If we extrapolate Voyager's trajectory using current orbital mechanics, we move from engineering timelines into geological and cosmological deep time.
Because it isn't stopping, it has achieved solar escape velocity. It's currently moving at roughly 17 kilometers per second relative to the sun. So, assuming it doesn't hit a rogue planet or a dense asteroid field, which is statistically nearly impossible given the sheer emptiness of the interstellar medium, what does the deep future look like?
Well, Voyager will effectively become a microplanet orbiting the center of the Milky Way. Its trajectory will mimic the sun's galactic orbit. Unless it passes too close to a rogue star and experiences a severe gravitational assist that ejects it from the galactic plane entirely, the models project it will complete one full orbit of the Milky Way every 250 million years.
A 250 million year here.
Yeah, and it's expected to complete roughly 100 of those orbits over the next 25 billion years.
25 billion years. I mean, the current estimated age of the universe is 13.8 billion years. Voyager is going to exist in its current macroscopic form for almost twice the current age of reality.
That is the physical endurance of the hardware. But even titanium and aluminum have a thermodynamic limit in deep space. Over incomprehensible scales of time, the spacecraft will face atomic attrition.
Right, it's not going to crash into anything, so how does it eventually break down?
Sputtering and micrometeoroid spallation.
How is that?
Well, the interstellar medium, while mostly empty, contains microscopic dust grains and highly energetic cosmic X-rays. Over eons, these impacts will slowly ablate the surface of the spacecraft. Physics models calculate that even if the craft loses only a few atoms per month to these microscopic collisions, over a timescale of 10 to the 28th power years, the entire structure will sublimate.
10 to the 28th power. I don't even know what prefix that is. It's an unimaginable stretch of time.
It will eventually disintegrate entirely, reduced to a vast, invisible, drifting cloud of mostly iron and aluminum gas.
A ghost of a machine. Which is haunting, but it forces a profound pivot in how we view the mission. If we accept the math, if we accept that this physical structure will outlast the Earth, outlast the sun's main sequence, and persist into the deep, dark, eternal future of the cosmos, then the mission is no longer about gathering telemetry. The mission is about the payload. What legacy did we actually bolt to the side of that spacecraft before we launched it into eternity?
Which brings us to the golden record, the ultimate message in a bottle.
Right. NASA knew Voyager was going to leave the solar system, so they convened a committee chaired by the astronomer Carl Sagan at Cornell University. And their mandate was staggering. Basically, distill the entirety of Earth's biology, culture, and history onto a 12-inch, gold-plated copper phonograph record.
Sagan himself maintained a pragmatic view of the record, though. He recognized that the probability of a spacefaring extraterrestrial intelligence intercepting a microscopic piece of metal in the expanse of the Milky Way was vanishingly small. He noted that the launching of the bottle into the cosmic ocean said something very hopeful about life on this planet.
So it was fundamentally a mirror held up to ourselves.
Exactly.
And what a mirror it is. The curation process was intensely rigorous. I mean, the technical challenge alone, how do you put pictures on a phonograph record in 1977?
They used an ingenious analog encoding method. The 116 images were converted into audio waveforms. Essentially, they took a video raster scan of an image, translated the light and dark pixels into high and low audio frequencies, and cut those frequencies into the physical grooves of the copper disc.
That's brilliant.
Right. If an extraterrestrial intelligence builds a playback device using the visual instructions etched on the aluminum cover, they can feed that audio output into an oscilloscope, and the changing frequencies will physically draw the images line by line on the screen.
It's a technological Rosetta Stone. And the content of those images is paired with a masterclass in sonic curation. You have the raw sounds of Earth, Mud pots bubbling, chimpanzees vocalizing, the seismic rumble of an earthquake, the rhythmic thrum of an F-111 aardvark flyby, the intensely intimate sound of a mother kissing her child.
And the musical selections reflect a deliberate attempt to avoid Western-centric bias. Yes, you have the mathematical precision of Bach's Brandenburg Concerto and the architecture of Beethoven, but you also have the raw, propulsive rhythm of Chuck Berry's Johnny Be Good, alongside traditional Navajo night chants, panpipes from the Solomon Islands, and the staggering polyphonic vocal traditions of Georgian choirs.
But the element that truly grounds the record in human history is the spoken greetings. They recorded greetings in 55 languages. At the time, those languages represented about 4.7 billion people, which was the vast majority of the global population.
And what's fascinating here is they didn't merely select the dominant political languages of the 1970s. The linguistic depth spans millennia.
That is the most striking part to me. They went to the linguistics departments and recorded greetings in dead languages: Sumerian, Akkadian, Hittite, Aramaic. They sent the voices of ancient Mesopotamia into the galactic core. And the tone of these greetings is so deeply moving. There's no bravado, no posturing. When you listen to the Amoy speaker, which is a dialect of Southern Min Chinese, the translation is utterly domestic and profoundly welcoming. The speaker just says, "Friends from space, how are you all? Have you eaten yet? Come visit us if you have time."
Have you eaten yet is the absolute bedrock of human hospitality. It transcends culture. To engrave that sentiment onto a vehicle capable of interstellar travel demonstrates a level of vulnerability and optimism that is incredibly rare in state-sponsored scientific endeavors.
And you see that optimism heavily layered into the political artifacts on the record, too.
Yes, the printed messages from U.S. President Jimmy Carter and United Nations Secretary General Kurt Waldheim provide vital historical context. Carter's message explicitly acknowledges that we are a divided, flawed species, yet it states our hope to survive our time, to resolve our differences, and to eventually join a community of galactic civilizations.
You really have to view that through the lens of 1977. We were deep in the Cold War. The threat of mutually assured nuclear destruction was an everyday ambient reality. So to build an interstellar probe and literally print the hope that we won't blow ourselves up before we reach the stars, it's a profound act of defiance against the cynicism of that era.
It was an assertion of continuity. But for all the polished political messages, the carefully selected music, and the polite greetings, the curation team understood that art and language are just outputs. They wanted to capture the engine itself. They wanted to encode raw, unfiltered, biological humanity.
Which brings us to the most emotionally resonant piece of data on the entire Golden Record. This is the absolute core of our deep dive today: the mind of Androyan.
Androyan was the creative director of the Golden Record Project. Her role was pivotal in gathering the sonic and visual tapestry we just discussed, and her personal integration into the physical data of the record represents this fascinating intersection of neurology and philosophy.
The technical challenge here is mind-bending. I mean, I understand how you put a microphone in front of a choir to record audio. I understand how you use a raster scan to turn an image into frequencies. But how do you capture a human thought? How do you map the actual cognitive biological process of a mind and etch it onto a copper disc meant for a non-human intelligence?
The methodology was aggressively innovative for the 1970s. Druyan went to the neurology department at Bellevue Hospital in New York City. She volunteered to be the singular biological representative of the human species. The medical team hooked her up to two primary arrays: an electroencephalogram, or EEG, to measure the microvoltage fluctuations of her brainwaves, and an electrocardiogram, an EKG, to monitor the electrical pacing of her heart.
So they are pulling the raw, organic electrical signal straight from her central nervous system and her cardiac muscle.
Well, exactly. Those biological voltages are dynamic. The spikes and troughs of the EEG and the QRS complex of the EKG were fed into a computer system equipped with voltage-controlled oscillators. As the voltage from her brain increased or decreased, the oscillator changed the pitch of an audio tone. They mapped human biology directly onto the audio spectrum. She sat there for an entire hour, meditating, while the machines translated her life force into a continuous, shifting drone of sound.
But the Golden Record only had a few minutes of real estate left-right. They couldn't put an hour-long drone on the disc.
No, they utilized time compression. That full hour of continuous neurological and cardiac audio was compressed down into a single, dense, 1-minute track. If you listen to it, it sounds like a rhythmic, almost aggressively abrasive burst of static electronic chirps and shifting frequencies.
But it isn't static. It is pure data. And the data isn't arbitrary. She didn't just sit in that hospital bed staring at the ceiling. She arrived with a meticulously prepared mental itinerary. She knew that her cognitive focus would alter the voltage patterns of her brain, so she orchestrated exactly what she would think about minute by minute to ensure the data accurately reflected the human experience.
Right. Her mental itinerary was a monumental philosophical undertaking. She deliberately shifted her cognitive load through the history of the Earth, the evolution of biological life, and the complex architecture of human social structures.
And she refused to sanitize it. That is the duality of the Golden Record that I find so compelling. When confronted with the task of presenting humanity to the cosmos, the instinct might be to only show our best angles. But Druin focused intensely on our profound flaws. She concentrated on the violence of our history, the brutality of war, and the abject poverty that, in her own words, makes this planet a hell for so many of its inhabitants. The neuroelectrical signature of her contemplating human cruelty is permanently etched into that gold.
The intellectual honesty of that decision is paramount. To launch a time capsule devoid of our capacity for destruction would be a massive misrepresentation of the species. The inclusion of our contemplation on poverty and systemic failure acts as a permanent confession, an acknowledgement that our civilization is deeply unresolved.
It's heavy. It is a heavy cognitive load. But here's where it gets really interesting. The climax of this entire process, the part that genuinely gives me chills every time I review the historical logs, happens at the very end of that hour. Toward the end of the session, after navigating the trauma and the history of Earth, Drian permitted herself a deeply personal mental excursion.
Yes, the shift in tone.
Right. Just a few days prior to this hospital visit, during the chaotic, sleep-deprived rush of compiling the record, she and Carl Sagan had a phone call where they finally admitted their feelings for one another. They decided, essentially on the spot, to get married.
It's incredible.
So sitting in Bellevue Hospital, wired to the oscillators, her brain buzzing with the history of the world, she spent the final minutes of the recording session simply thinking about what it felt like to fall in love.
And the neurological shift from that heavy historical cognitive load to the limbic emotional resonance of falling in love is permanently captured in the frequency shifts of that compressed audio.
When you synthesize the physics of the mission with that biological reality, the result is staggering. We talked about the 10 to the 28th power year timeline. We talked about the sun expanding into a red giant and boiling away the oceans, erasing every physical monument we have ever built on this planet. But out there, 25 billion kilometers away and traveling endlessly into the dark, the exact neurological and cardiac signature of a human woman contemplating the tragedy of poverty and the absolute ecstasy of falling in love is perfectly preserved.
It is the ultimate bridge between the cold, indifferent mechanics of astrophysics and the warm, beating heart of biology. I mean, we constructed a machine out of titanium, powered it with decaying plutonium, and sent it out to measure magnetic shock waves in the interstellar plasma. But tucked inside its chassis, we hid the raw electrical voltage of human love.
It is poetry encoded in physics. And just as the Golden Record was humanity broadcasting its spirit outward, Voyager's other profound legacy came from its ability to look backward.
The family portrait maneuver. Specifically, the pale blue dot.
Yes. So, jump forward to 1990. Voyager 1 had long finished its primary planetary flybys of Jupiter and Saturn. It was pitched high above the ecliptic plane, heading out of the solar system. Carl Sagan, working alongside the planetary scientist Carolyn Porco, began an intense lobbying campaign at NASA to turn Voyager's cameras around and take one final photograph of Earth from the outer edges of the solar system.
And the resistance from the engineering teams at JPL was substantial and honestly justified. Pointing the highly sensitive Vidicon camera tubes back toward the inner solar system meant pointing them perilously close to the sun. There was a high probability that the intense solar radiation would permanently blind the optical sensors. Furthermore, from a strictly scientific perspective, the image would yield zero new telemetry. Earth would resolve as less than a single pixel.
But Sagan argued the philosophical mandate. He argued that the perspective gained by seeing our planet as a microscopic speck against the void would be a transformative cultural artifact. And NASA Administrator Richard Truly eventually agreed, overriding the engineering concerns. So on February 14, 1990, the command was executed.
Voyager 1 was 40.47 astronomical units away, over 6 billion kilometers. It executed a complex mosaic of 60 frames to capture the planets, but the frame containing Earth is the defining image of the mission.
The mechanics of that specific photo are crucial to understanding why it looks the way it does, because it isn't just a point-and-shoot snapshot.
No, the imaging system utilized the narrow-angle camera, which was a 1500-millimeter catadioptric Cassegrain telescope. The camera took 3 sequential exposures using 3 distinct colored filters: blue, green, and violet.
And when the data was downlinked and recombined at JPL, Earth took up exactly 0.12 of a single pixel, just a fraction of a point of light. And it's caught in this massive sweeping beam of light. I think a lot of people initially look at the photo and assume that beam is some kind of cosmic spotlight shining on Earth. But it's a physical artifact of the camera hardware, isn't it?
Yes, the prominent bands of light stretching diagonally across the frame are stray light artifacts. Because the camera was pointed so close to the sun, the intense sunlight scattered and reflected off the physical hardware of the camera's sunshade and optics. Earth just happened to serendipitously fall precisely within the center of one of those scattered light rays.
A beautiful optical accident. But the color of the dot itself, that pale blue that isn't an artifact, that is raw atmospheric physics. Why does Earth look pale blue from 6 billion kilometers away?
The blue signature is driven by Rayleigh scattering. As sunlight impacts Earth's atmosphere, the shorter wavelengths of visible light, specifically the blue wavelengths, are scattered in all directions by the nitrogen and oxygen molecules in the air much more efficiently than longer red wavelengths.
Oh, it's the exact same physics that makes the sky look blue when we look up from the ground. Voyager was just seeing our blue sky from the outside.
Exactly. And the crucial context here is that this intense Rayleigh scattering is a direct result of our specific atmospheric chemistry. We have a transparent, oxygen-rich atmosphere, which is entirely the byproduct of billions of years of photosynthetic life. If you look at Saturn's moon Titan, the atmosphere is thick with organic tholins, making it look orange and opaque. Because life on Earth oxygenated our atmosphere, it remains transparent to visible light, allowing that blue scattered light to reflect intensely back out into the void. The pale blue color is a direct, visual atmospheric signature of the biological engine operating on the surface, and the pale aspect comes from the white light reflecting off our water clouds mixing with the scattered blue.
It is the visual signature of a living world. And that image prompted Carl Sagan to write what might be the most vital piece of scientific literature of the 20th century. In his 1994 book, he looked at that 0.12 pixel dot, and he wrote this amazing passage. Consider again that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam.
It is a masterful weaponization of scale. He uses the sheer crushing volume of the universe to force a perspective of radical humility upon the reader.
I want you, the listener, to do an exercise right now. Think about the most pressing anxiety in your life today. A critical deadline at work, a geopolitical crisis you are reading about this morning, a bitter argument with a family member. Hold the weight of that anxiety up against the scale of that 0.12 pixel dot. Every war ever fought, every empire that ever rose and collapsed, the entirety of human ego and suffering, it all unfolded on a microscopic fraction of a single pixel. It doesn't render our lives meaningless, but it demands that we reevaluate our priorities.
It underscores our absolute isolation. As Sagan concluded in that same passage, there is no hint that help will come from elsewhere to save us from ourselves. The vastness of the dark around that dot implies a profound responsibility to deal more kindly with one another, because that pale blue pixel is the only home we have ever known.
Yeah. It is the ultimate grounding mechanism. So let's look at the totality of the journey we have mapped today. We started with the harsh, immediate reality of 2026. Voyager 1 is a degraded but fiercely resilient machine, amputating its own instruments like the LECP, relying on the heroic troubleshooting of engineers operating across a 46-hour communication void just to keep its core warm.
We charted its physical environment, crossing the termination shock, piercing the heliopause, and drifting out into the galactic ocean toward an orbit that will last hundreds of millions of years.
We decoded the Golden Record, exploring the ancient 55 languages and the deep political optimism required to send them. We navigated the Bellevue Hospital recordings, unpacking how Androian's raw neuroelectrical data captured the duality of human tragedy and the pure joy of falling in love. And finally, we looked backward with Voyager's cameras to see our entire existence reduced to a pale blue pixel.
This raises an important question, though, about the nature of the mission. When we examine the decaying hardware, the vast cosmic distances, and the biological data encoded on the record, we are forced to weigh the persistence of physical data against the persistence of meaning. If, billions of years from now, a non-human intelligence intercepts that copper disk, will they possess the neurological architecture to understand it? Will they be capable of decoding the time-compressed audio of Androian's EKG and truly comprehending the physiological state of human love? Or is the act of sending the record fundamentally solipsistic? Is it merely a monument we constructed for our own psychological comfort, a defiant shout into the void to prove to the universe that we were here and that we felt things deeply?
That is the ultimate existential tension, and it leads me to a final provocative thought that I want to leave you with today. We established earlier that in 10 to the 28th power years, Voyager 1 will succumb to the physical laws of the universe. It will be pulverized by X-rays and micrometeorites until it is completely sublimated into a massive, invisible cloud of iron and aluminum gas drifting through the absolute zero of an aging cosmos. But consider the atomic reality of that process. The atoms that will make up that drifting cloud of gas are the exact same atoms that were forged into a 12-inch copper disc and plated in gold. They are the exact same atoms that were physically displaced and etched with the microscopic grooves that represent the electrical signature of Anne Druin's brainwaves and her heartbeat. Even when the macroscopic structure of the spacecraft is completely gone, even when the record is reduced to individual subatomic particles, those specific particles will still carry the physical legacy of her thoughts. They are the artifacts of her meditation. In the deepest, most literal, physical sense, the manifestation of human love will outlast the physical existence of the universe as we know it today. So, what does that mean for you today as you go about your daily routine, knowing that human emotion has already achieved a form of physical atomic immortality out there in the freezing dark? Thank you so much for joining us on this deep dive. Take a breath, hold on to that cosmic perspective, and keep looking up.